Hi, so now it's time to take a look at the optics in this head unit. Now I've had a bit of a hunt around to try and find a diagram online. I've not found one of this exact one, but this is one which looks fairly close. And the casing is a different shape, so I'm guessing it's probably from a slightly different version. And this doesn't appear to have the Acousto-optical beam splitter. It looks like it's got a an array of manually selectable filters down here, but apart from that it looks reasonably similar. So you've got the various lasers coming in, both from the big box of lasers, but some external, some separate ones as well. There's another diagram in the user manual that shows all the various options. The general idea is that the light from the lasers goes down and is scanned in X and Y axes, but also rotatable down into the sample. The sample then fluoresces, the light comes then back up, back through the beam splitter, through a polarization wheel, then across into a prism, then down into some adjustable slots, into one of several photomultipliers. Okay, let's see if we can figure out roughly what's where on this, going by that previous diagram. We know the laser comes in here from the box of lasers, and here obviously is the Acousto-optical beam splitter, so this is where the light path is split between the light going down towards the sample and coming back up for analysis. And so it goes down here. There's the main exit port, looks like it's down on the right here, so there's probably down here there's this scanner. We know there's a galvanometer on this section, this whole sort of rotating section. Then it sort of goes back through the beam splitter up to, this is the additional port for potential other lasers. This will be the Prism, I think. Then it goes down to these motorized slits, and then the detector assemblies. There's one here and then one on the back for the photomultiplier detectors. There's also a piece that comes out forwards here, and then there's sort of an angle that pointed up this way, so I'm not sure if that's another entrance port for another device or detector or some other option, but not quite sure. But so unfortunately I can't find a drawing that exactly corresponds to this, but I think that's sort of roughly right, so I think we need to dive in and see what's going on in this thing. Take this top bit, we can see this in the diagram which shows red and green lasers going in here, and if we shine some white light in the bottom we can see the red and green outputs. There's only one fibre coupler on there, but there's clearly a footprint here for a second one of these fibre optic couplers, so again that's an option that's not fitted. And then here in the centre section we can see these are presumably the wavelengths, so I'm getting band pass and I'm not sure, band select perhaps, so 500 to 550 which would be the green, 607 to 683 which would be the red, and then SP700, not quite sure what that's going to be. There's probably some other filters. There's also a shutter in here as well. You can just see the rear of the motor on the shutter, which is sort of partly open. Doesn't seem to want to gravity close, but again I think this had actually been bashed off because the threads did seem to be quite chewed, and this was just separate floating around in the unit, so I think this was just on its side, it's probably just got knocked, or the whole thing rested on it in naked. And this is clearly a removable section, so depending on which lasers you replace this, and this has actually got the filters in there. Interesting, that one looks like it's had some damage over time. Again, it may have been, this might have just got wet, it might have been water damage or something, so we've got a... yeah, so the green passes straight through that mirror, the red gets reflected by it. Another little detail of design overkill, just to run this wire down here. They've actually sort of machined out a section and done this little plate that screws in, whose sole purpose in life is to keep this wire hidden. Most people would just use a cable tie. So this is the polarization filter wheel, which, as you'd expect, is a wheel with a polarization filter. We can prove that if I just look through an LCD. Rotate it, it rotates the wheel, so that's selecting a particular polarization. It's a nice little motor, I think that's probably a stepper, and there's you can see there's a interrupter to get zero reference. there, and just a little ball with some diodes and PTC protection on it. And there's also positions for some other filters, of which there is one filter fitted. In here there's another motor assembly, which is very difficult to get out because of the shape. There we go. Oh, so this looks like it's a motorized assembly that can put one of 3 mirrors in, I think. Yeah, so we've got a fully reflective mirror. There's a, I don't know if that's a partially reflective or a filter or something, but there is definitely some sort of glass in there. And that one's blank, and that one actually passes straight through. Oh, actually yes, because this is where that external beam port was. That could do straight through to allow the beam to go straight through that way, or it could reflect it that way, or it could do a partial reflection, so some went that way and some went this way. So that's a sort of just a 3-way selector. Right, there's something behind this panel here. Instead, I've taken out the Acousto-optical beam splitter module. I'll take a look at that later. And this appears to be a little motorized iris. As I turn that motor, you can see there's these 2 blocks there and a sort of cam that operates them. So as you can see, as that rotates, that central hole gets larger or smaller, so that's probably just a sort of beam attenuator or something. And there's a piece here, it looks like it's just a fixed lens or something. There's a lens there, but there's also an adjustment, so it looks like you've got a sort of solid piece of aluminium that's acting as a spring, and then this there's actually another spring here, and a couple of adjustment screws. So this screw sort of pushes it that way, and this adjustment screw sort of levers it so that moving that screw will adjust it that way. So that's obviously a very fine adjustment lens position in the beam path. And behind here we've got the prism. And you can see this prism's on a precision adjustable mount as well. There's a in here, this is actually just a solid piece of aluminium that's just been machined out to form this central section. There's these adjustment screws that just apply force to this platform to adjust the prism angle precisely. And you can see how this prism splits up the white light into its pretty constituents. And down here in the detector we've actually got 3 motorized slit assemblies. So we've got 2 tiny little motors, and I think the way this works is one of them moves the whole assembly backwards and forwards, because this second motor looks like it's actually mounted on a moving assembly, and then the second motor actually adjusts the slit width. So this basically sets the wavelength, and then the slit effectively adjusts the spatial resolution. I'm assuming there's one of these for each of the photomultipliers. I can't quite figure out the exact optical path here, but say this one's got 2 sort of slopey mirrors, and this one, they're parallel. And I think, yeah, this other one down here is also parallel, but so the fact 3 of these and 3 photomultipliers, I'm sure there's one for each. Okay, I've finally figured out how this works. I'm just shining a super bright LED through here, prism back in, so we can actually get a spectrum. These just happen to be in a sensible position to actually produce something. So the light comes down here and it hits these 2 mirrors, which are adjustable for position, and basically what that does, deflects one end of the spectrum up this way, so we've got sort of red to green here, and that goes into this top detector. The part that goes to the centre goes down this gap and into this bottom detector on this side, and the other mirror reflects up in this direction, so into this detector here. Now this bottom sensor must have been the one that wasn't fitted, because there's no light goes in that direction. And then these other two slits further cut that light. So if we stick this one back in, you can see a small amount of the light, a very small section gets through there, and again that's adjustable. Similarly, this other one does the same thing for the other side, so each side can, it looks like you can basically do like a high pass and a low pass, and then sort of then filter that subsequently to get all sorts of different permutations of filtering on the light that comes through. Again, I don't know too much about what the actual requirements are for this, but so you've got these various options. By adjusting these slits you can measure various things. I mean, this, you could probably modify this quite easily to make up quite a nice spectrometer. I suppose if I've got nothing else better to do, I might have a go at some point. Right, now moving down to below the Acousto-optic beam splitter. I've got these two big stepper motors. And you've got this assembly which rotates one of three optical assemblies. There's a multi-lens assemblies that may be perhaps collimators or something. These are sort of precisely alignable on both ends. You can see the alignment screws are accessible through those holes. Even so, it's probably a bit of a fiddly job to align that, I would imagine. Okay, now down to this rotating part. Now the light path here, this is sort of the downward path. So this comes down and gets reflected to the right by this little mirror here. So this is now sort of going horizontally that way. I think I'm going to have to take this a bit further apart to see exactly what's going on. There's a few sort of couple of mirrors up here and something going on here. So I need to, I think, get a bit further into this to figure out what happens next. Okay, this makes a little bit more sense. So I was a little bit puzzled about what's happening with this galvanometer here, because the mirror that takes the beam path into this section sort of seemed to just disappear, sort of go into here. I can figure out, well, how can that be doing anything? What's actually happening is we've got this whole rotating thing, but then the galvanometer can then rotate this part and sort of scan in this direction. So we've got sort of an overall rotation, and then the actual scan part of it. Now there's another, I'm not sure if this is an actuator or not. If so, it could well be that these two galvos gives you the XY raster scan, and this rotation just provides a way of just rotating that whole raster. Not quite sure why you'd do that rather than just rotating the sample on the stage, but I think that's the case. So we've got basically a rectangular scan. Bear in mind, of course, because these are scanning small samples, the actual amount of scan is going to be very small, because we've got, you presume, some distance between this and the sample, but obviously you're scanning very small samples, so it's probably only scanning like a millimetre or two range. So I'd imagine when it's running, this probably sort of moves only a very tiny amount to produce that scan. In fact, what I should probably do is just whack a laser into this and manually operate this. I should be able to get a clear idea of how it scans. Let's try that. Just took the red helium neon laser up along with this mirror to actually get it down into the right place. So I've lined this up and I've hooked the coils of the galvos to the signal generator just on the sine wave. The Y and the X, and together we have the inevitable Lissajous figure. If I just rotate the stepper, you can see it just does, this isn't completely lined up for rotation, but so it just rotates the scan around. There's probably the fact it's not rotating around the centre is probably just the way I've lined it up. These galvos do need quite a lot of control if you actually want to get accurate scanning. Things like laser displays, they've got internal optical feedback, position feedback, so you actually need to create a sort of proper servo system to actually get them to go do an accurate position. So I can change the waveform shape on here, but it's very much determined by the dynamics of the Galvo. This is running at 60 Hertz. And there's the little circuit on the back of here. This is the amplifier for the feedback. So there's a photo diode and an optical arrangement in there that gives you a signal that tells you how far around it is. This little one here, it's a moving magnet, so it's basically a magnet with the coils around it. Applying signal to the coils makes the magnet move, but say because of the dynamics you need to have a closed loop feedback to actually get it to move sensibly. And of course this in combination with the acousto-optical things means you could actually get quite a nice sort of modulated laser system going. I don't know whether the speed of the acousto-optical stuff in these scanners are actually comparable to the sort of thing they use in sort of laser show type projectors. I think one issue is the axis that's driven by this rear one is very heavy because it's got that fairly big metal block to support the rotation and so on, so I doubt you'd get a particularly fast scan rate in that axis, but the other one's got a tiny little mirror, so that's probably a fairly fast little unit. This is the smaller of the galvanometers. Sort of I think just this back bit is the motor, although it might extend up here, I don't know. See a bearing and some end stops and the mirror on the end. And this is, I've just got this running at 10 Hertz. You could probably do some quite fun things with this in combination with a sort of rolling shutter camera to get some bizarre effects. Increase the frequencies is probably going to do some weird strobing things with the camera. The datasheet says it's got a settling time of 300 microseconds, but obviously that needs a proper sort of servo control to achieve. This sort of seems to vibrate. The amplitude dies down quite rapidly above about 200 Hertz. So looking at the actual light path in here, the beam comes in here horizontally, hits this mirror and then this mirror, and if you look at the way these are mounted, these are both mounted on this central section. So this is now sort of swinging the beam that way, and then that directs it onto the small galvanometer motor, which is right under here in the centre. And then if I just rotate the body of this galv, you can see that's basically lined up directly with the output. I don't think there's much to be going on, but obviously I'm not going to take these galvos apart because these are quite useful things. I'm going to leave this assembly as it is for the moment because it might be easier to line up if you want to try messing around with this in conjunction with the acousto-optical bits. So I'm going to leave this as a single assembly for the moment. And the final part of the puzzle, this is the acousto-optical beam splitter module, where all the magic happens. And there's a couple of acousto-optical parts here. There's this one at the top, and you can see there's the RF input there goes through a coil. That's probably a matching network onto the side of the magic crystal, and the beam path on here. Basically the beam comes in here, gets reflected at right angles, and on the back of here there's a photodiode, so that's monitoring the beam power coming in. Then goes across here, hits this mirror, and then goes down into the unit. And there's another little mirror that's a bit hard to see, it's a fairly small wedge down there, which reflects it downwards through this crystal. It's not clear whether these crystals are similar. I think this one might be the magic one that actually does the beam splitting. I'm not sure if it's the same type as this, whether it's a one of these tunable wavelength things or it's something slightly different. Comes out the bottom, that then gets reflected back to the fluorescent signal, which is at a different wavelength, which is the one that wants to be separated out. Goes back through this same crystal, then up, hits this top crystal, passes through, and then there's a little pair of mirrors that act like a sort of periscope just to shift this back down again, back to the original beam path, and then out. So I suspect that because one of the diagrams I found showed just a moving filter assembly, I think this is a replaceable module, so they want to keep the beam path the same, so they could either put a set of standard filters in or put this module in, depending on what the customer ordered. Because I'm guessing this is probably quite a lot more expensive than a set of filters, so the customers that need the flexibility of easily selectable wavelengths stick this in. So they've put this little periscope thing in there because as the beam goes through the crystal, it gets deflected sort of sideways slightly, so this is probably just to recorrect that to keep the beam in line. So they've got the same optics for both versions of the product. And there's a couple of little boards on here. I'm certain these are going to be temperature sensors. They've just got a little SOT23 and a switch, which I'm sure will be setting the I2C address. So you've just got a couple of temperature sensors, one for each crystal there. And I'll be firing this lot up and having a play around with these optical stuff in a separate video.